Hi there, I'm Matt Layher. I'm a software engineer at DigitalOcean, and today I'm going to be talking to you about how we manipulate OVS with the Go programming language at DigitalOcean. Oops, sorry, clicker. There we go, perfect. So I've been a software engineer at DigitalOcean for about 3.5 years now, primarily focused on our virtual networking primitives. I'm a huge fan of the Go programming language, and also you can find me on GitHub and Twitter at MDLayher. So I'd like to introduce you to DigitalOcean for those who aren't familiar. DigitalOcean is a cloud provider with a focus on simplicity. So we really strive for simplicity above all else. Our Droplet product is a virtual machine, but we also offer compute, storage, networking, and monitoring primitives. For networking, we offer features like load balancers as a service, floating IPs, and cloud firewalls, which my colleague Kei Noguchi talked about yesterday. So DigitalOcean is powered by vSwitch. We have more than 10,000 instances of OVS in our fleet, and it's one of the most crucial components in our entire stack. So first, I'd like to talk to you about how we used vSwitch at DO in the past. To start, we used vSwitch with Perl. A lot of our backend code at the time was written in Perl. So in this scenario, events such as creating a droplet, powering it on, powering it off, what have you, reached a hypervisor. And these Perl event handlers pick up these events and perform some series of actions to prepare a droplet for existence. Finally, Perl builds a series of flow strings and calls out to the OvS CTL tool. So our flow rules looked a little like this. And I apologize, I hope the code comment color is OK. So here we have an array of flows, and we have each element of the array has a flow priority, a hash of key value flow matches in the OpenFlow format, and then a literal string of flow actions with a little bit of string interpolation there. And in this array, there are many flows. So once we have that flow structure, we actually construct the matches into a single string. We build an entire flow command with a priority, an idle timeout, the series of matches and actions, and then we add a flow deletion hook to libvirt. And this is necessary so that when the VM powers down, libvirt can trigger our commands to remove some of our old flows. And this was OK, but a little problematic in some ways. Finally, we shell out to the OvS CTL command, and it does the work. And it adds the flows to the specified bridge. So this was great. The pros were the code was pretty straightforward in general, and Perl's really good at manipulating strings and shelling out to other utilities. As far as cons, there was no real sanity checking other than OVS trying to apply the flow. So it was easy for typos and other problems to occur. The test coverage was a little bit lacking, but that's kind of on us as well. The libvirt flow deletion hooks I talked about were a little bit problematic with individual flows, and we would have dangling flow problems at times. And finally, we had to shell out once per flow. So there was no atomicity to this approach. So if we're adding 50 flows and you fail on flow 25, well, you've kind of got a mess. So let's talk about where we are today with vSwitch at DigitalOcean. So today, we primarily use vSwitch with the Go programming language. In this scenario, events reach a hypervisor, and then Perl or Go, depending on the system, picks up these events and performs some series of actions to prepare a droplet for existence. Finally, Go builds flow strings and calls out to OvS CTL, much in the same way. So first, I'd like to introduce package OvS. And this is our client library for vSwitch. And it enables programmatic control of the virtual switch from the Go programming language. So this is a Go package for manipulating OvS, but it contains no DigitalOcean-specific code whatsoever. You can see the GitHub link here, and it's not open source yet. We're waiting on final approval, but it should be very soon. And we've been using this for roughly 2 years in some form or another. So this is a little bit of what our flow structures look like in Go. So we have this OVS flow type. And some of the commonly used pieces in the flow are these structure fields here, things like a priority, a protocol, or an import. And the match and action types are actually Go interfaces. So we have these functions that create types that implement the interface. So as an example, you've got something like data link source or network source matches and a resubmit action. So that example flow marshaled to the textual format looks something like this with some mock data. So behind the scenes, this is mostly still string manipulation, just like Perl. But since Go is statically typed, we can reduce the chance of programming errors by verifying things like an IPv6 address can only be used where one is expected, or you can't use a MAC address in a field that expects like an IPv4 address. So this is great. We can validate our matches and actions without actually touching OVS at all. So this is our match interface. So because of the way Go interfaces work, any type with this Marshall text method can be used as an OVS match. So the error return value from this function is used to catch any bad input when we're creating the flow strings. And the definition of the action interface is actually identical as of now, although we haven't really had trouble mixing the two up in our code. So if we want to put this all together and actually manipulate the switch, we have this client Go type. So our client is a wrapper around OVS vSCTL and OVS OFCTL commands. So the vSCTL commands are exposed via this vSwitch member, and the OFCTL commands are exposed via the OpenFlow member. So in this case, the vSwitch add bridge call with an argument of bridge 0 would actually shell out to OVS vSCTL add bridge 0. And the OpenFlow add flow call, you specify an input bridge, and then you can add flow. You've got a couple of arguments in there for things like our flow format and our protocols. Finally, you specify the bridge, and it will actually take the flow and convert it to the string format. So this is great, but we can still only apply one flow at a time, right? This is where flow bundle transactions come in. And when we discovered this feature in OpenFlow 1.4, we knew we wanted to use it immediately. So let's say we want to apply some new flow set and remove an old one from one of our virtual machines. So we can apply all of these atomically using a flow bundle. And that's where this add flow bundle method comes in. You specify the bridge you want to work on, and it creates this flow transaction type within the context of a function. So inside this function, you can push flows for addition and push flows for deletion. And what this is essentially doing is creating these strings in memory and pushing them into a buffer. Finally, when you call the commit method on the transaction, it opens the buffer, pushes it into the standard in of OVS OFCTL, and executes all of the commands at once. And OVS is able to process it in a single atomic transaction. So now that we've introduced some of the basic primitives, let's get to the higher level interface that we use every day at DO. So package HPFlow is our Open vSwitch flow manipulation package for the hypervisor level. This is a DigitalOcean specific wrapper for the package I talked about earlier. It provides some higher level constructs for our environment, things like enabling public IPv4 and IPv6 connectivity to a virtual machine, resetting and applying security policies, or finally, disabling all connectivity to a virtual machine. So this is our client's type. And the HPFlow client is a high-level wrapper around the OVS client. And the HPFlow client, similar to the OpenFlow, or the OVS client, excuse me, uses a functional options pattern of sorts so that you can specify optional configuration parameters for all of your dependencies. In this case, we configure the OVS client with the OpenFlow format that we expect. So now that we have this client type, if we want to actually manipulate the switch, we have this high-level internal network parameters or netparams structure. You'll see a JSON representation of it on the right. And this is some of the data that we store, construct, and pass around in our infrastructure to enable connectivity to various virtual machines. So these encode all the data we need to enable networking for a VNIC. And in our case, these carry things like IPv4, IPv6 addresses, firewall configurations, floating IPs, and various other data. Finally, we use this netparam structure to configure OVS with our client's transaction method. So let's assume we have some netparams structure similar to the one we have just shown. We want to enable networking on our public interface. So we call this transaction method, and it opens up a transaction with this HPFlow transaction type. Within the context of the transaction, we are able to parse out the information we need to, say, enable IPv4 connectivity on a public interface. If the netparams contain valid data for performing that operation, we call these high-level operations, such as tx.enableIPv4, to actually build the flows in memory and concatenate them into that buffer. Finally, we call the commit method, once again, to flush the entire flow set to OVS all at once. So each operation within the transaction accumulates additional flows. And we have a set of example operations on the right, such as enable IPv4, enable IPv6, enable floating IPv4, disable connectivity, or commit the flow set to OvS. And our flow set sizes can vary from a couple dozen to several hundred flows per virtual machine, just depending. Finally, it's worth noting that our flows are always applied using a flow bundle. We had a non-transactional API before we started using OpenFlow 1.4, but we actually removed it because it just wasn't as useful or safe as the transactional API. I'd also like to talk about our cookie interface. So we make use of OpenFlow cookies, that unsigned 64-bit integer format, in the form of this Go interface. So we have structures that implement the interface, and they're packed and unpacked from the unsigned 64-bit integer form. Our cookies are versioned using a fixed 4-bit identifier, so it's easy to upgrade in the future. And we use these to store identification metadata about a flow, things like a resource type, a resource ID, an interface index, or whatever else we need to do. Finally, these allow us to easily delete large swaths of flows with much simpler deletion hooks than libvirt. So now that we have these two packages put together, I'd like to introduce you to the programs that actually make use of them. So we have HPFlow CTL and HPFlow D. And these are gRPC client and server applications that manipulate Open vSwitch. So these are both written in Go, and they use gRPC, which is an HTTP2-based RPC protocol based on protobuf primarily. HPFlow CTL passes net params and other data to HPFlow D, and then it's HPFlow D's job to actually manipulate the OVS flows using the HPFlow package. So this is an example of one of our RPCs, the addFlows RPC in particular. It accepts an addFlows request and returns an addFlows response. Within the addFlows request, we have our network parameter structure encoded in protobuf format and a specific interface type as of now. There's no need to return any data on success, so we just return this empty message. So now, once we pass these through the Go protobuf compiler, we actually generate a generated interface in Go that has this method addFlows with this signature. So we have our internal server type that implements that interface. And as a result, our server can receive RPCs over gRPC. It just works. So if we want to actually add flows to a droplet, we fetch the net params from the gRPC request message, and then we perform whatever transaction logic is necessary to establish the connectivity. Those could be some of the high-level operations I talked about earlier, like enable IPv4, enable IPv6, and what have you. Finally, we commit the transaction, and the changes are either applied to OVS completely or not at all. The key point here is that these RPCs enable us to orchestrate among multiple hypervisors and HPFlow D instances. So now that we've introduced these two daemons, how do we test them? Well, we have a series of unit tests that verify our flows look a certain way. So given some set of inputs and some flow structures, we can verify that we produce the correct flow strings. But that doesn't actually validate the semantic correctness of the flows necessarily, or the fact that they could establish connectivity. So we have a series of integration tests that verify the behavior of flows we apply to OVS. And for this, we use Mininet, OVS, HPFlow CTL, and HPFlow D. To test with Mininet, we spin up this network topology with multi-namespace OVS. An HPFlow D instance is spun up in each hypervisor namespace. So we create it in the background and export a series of environment variables from a configuration to configure the daemon. Finally, we tell HPFlow CTL where to find the daemon using the RPC flag, and it issues RPCs within that context using JSON net parameter fixtures that we specify for our tests. When you put this all together, we build a Docker image and push it up, and it's pulled by Concourse CI. So we spin up this virtual droplet and hypervisor topology, and then we run tests on every pull request to the HPFlow package. So every single change, we can verify things like internet connectivity to a public interface or floating interface works, but internet connectivity does not work to a private interface. So what can we conclude about this approach? Well, Go is really well suited to building large, highly concurrent network systems. And in general, it's just a pleasure to work with. It also compiles to a single statically linked binary for trivial deployment, and the flows are easier to read for those who aren't familiar with OVS. The data is statically typed and checked before hitting OVS, and we can also bundle the flows and commit them atomically. As far as cons, the flow structures are pretty verbose if you're familiar with OpenFlow and OVS, And underneath, we're still shelling out the OVS tools as of now. It's only an incremental upgrade. So where would we like to go in the future with Open vSwitch at DigitalOcean? We'd like to move to an orchestrated Open vSwitch and Go approach. So an RPC would be performed to some regional network service, and the regional network service determines some series of actions and sends RPCs to one or more HPFlow D instances, depending on what's needed. Finally, HPFlow D builds a series of flows and speaks OpenFlow directly to OVS. So what are some of the use cases for this orchestration system? Well, in our environment, we want to be able to provide high-level networking actions that apply to many hypervisors and their droplets. Things like we want to apply a cloud firewall that says open TCP port 22 to all droplets for customer X, or we want to disable connectivity to all droplets for customer Y. And why speak OpenFlow directly? Well, we've had some difficulty parsing the unstable OVS tool text output, as you might imagine. In particular, this dump ports call is a little bit problematic. Although I understand in OVS 2.8, we can actually use port names directly instead of port numbers, which is going to be fantastic for us and save us a lot of effort. There's also some tedious generation and parsing of these flow strings in general. So we'd like to remove that and speak OpenFlow and use a more sane binary format. So why not just use an OpenFlow controller? Where we are right now, it seems like the industry is moving to a distributed control plane approach. And in our architecture, we need to be careful to avoid any scenario where it might be difficult for us to scale a central controller in one or more of our data centers. We did consider OVN, but at the time, we were concerned about its maturity. And we've implemented a couple of strange things in our environment that don't map well to OVN concepts as of now. And our RNS architecture is actually very similar to OVN in a lot of ways. Finally, a distributed OpenFlow controller of sorts is not off the table. So perhaps HPFlow D could become OVS's controller. Or as I learned last night, we could possibly run the OVN controller daemon and then use HPFlow D to program that in our environment as a way to kind of step into both worlds, which could be pretty interesting as well. So if we wanted to add OpenFlow support to our client in this case, let's say we just add a new option. So we have this Use OpenFlow option that toggles on direct OpenFlow support. The high-level interface remains exactly the same. We still have our structures, but we would just marshal the flow to the binary format instead of the text format. In this case, our match interface and our action interface both gain new methods. So we have this text marshaller, marshal text method, but we'd also have this marshal binary method as well. And we just need to implement this for all of our match types to spit out the equivalent OpenFlow. The action interface would be updated in exactly the same way. As far as conclusions about this approach, it's really too early to tell, but in theory, it will be easy to orchestrate changes among multiple servers. We won't have to parse the OVS tool string output at all, and we won't have to generate and parse the flow text format, which we probably shouldn't have been doing in the first place, but it's worked really well so far. So what can we conclude about Open vSwitch at DigitalOcean? We love Open vSwitch. We've deployed more than 10,000 instances of it, and we've run it in production for 3 years now. We've moved from Perl to Go, and even though it's been kind of an incremental change, our OVS tooling has gotten a lot smarter over time. And finally, we're really excited for the future of OVS and OVN, and to be part of it as well. So thank you very much for your time, and I look forward to answering your questions.
Thank you for the talk. We do have time for questions. One question I have is, it looks to me like there's something missing from your match and action interfaces. Shouldn't there be unmarshal methods?
Yes, yes, there should be, but we actually do that in kind of an interesting way now. I have a couple of little hacky things when we were originally implementing the system that will take the string format and parse it out, but it uses like regex and other nasty things. So it's not really officially a good idea, but yes, it should be there in theory.
Okay. Bob?
So I'm not really opposed to constructing command lines and sending the tools. That's what Mininet does. But I think your whole story sort of describes why having a network controller API is really a good idea and how it's actually useful. And so I guess my perhaps comment to you is that I think it'd be something like that is actually valuable to have it in Go. That is to say, a network control, basically a network controller framework that speaks two southbounds at least. One is OVSDB to configure OVS, and the other southbound is OpenFlow to put flows in. And also, I sort of like how you sort of seem to be aimed at creating a user-friendly both configuration and flow control API, and I think having that in Go is really useful. Because another thing is, I don't know if something like Loxygen can generate the low-level sort of OpenFlow driver for Go, but that would be another useful thing. Certainly, it can currently generate, I think, C and Java. I don't know if it generates Go, but that's perhaps would also be a nice thing that I think the whole like OpenFlow and SDN community would benefit from. Would be something that automatically generates from essentially the OpenFlow spec or a machine parsable representation of it, generates the low-level APIs, and then you can make your beautiful user-friendly Go API, which would also be a great contribution to the OpenFlow community. And SDN.
Yeah, absolutely. So that's kind of, I mean, we've done a very, kind of very basic versions of that, but as we discussed with the OVS and OVN teams, we could potentially have something that generates the OVN format, which is more friendly, and then we can integrate easily with OVN as well. So there's a lot of possibilities here. This is just what's worked well so far, because we kind of wanted to stick with the same approach moving from Perl to Go, at least initially, but we gave ourselves a little bit of room to be flexible too. So yeah, it's exciting. And of course, we want to open source as much as we can. Please keep an eye on this repo. I hope to have that code out in the next week or two. So, yeah.
So you might not know, but Bob, who was asking the question, he's the author of Mininet.
Oh, really? Oh, that's excellent. Well, yeah, thank you. We appreciate it.
Like Ben, I always like hearing from users because similarly you don't know who's using it, so it's great to hear it. Thanks.
Excellent. Well, yeah, thank you for mentioning that. It's been pretty crucial for us.
All right, we have time for more questions. Would anyone like to ask a question? I think it's conference fatigue.
Yeah, absolutely.
All right, let's thank our speaker one more time.
Well, thank you.